Bismillahirrahmanirrahim. We are going to start the first question of a new exercise. This exercise is about determinants. So while going through these questions, we are going to cross our paths with a lot of properties of determinants. So as the first one is used in this question, first of all, we are going to write it as it is equal to. We can see that the first column has 9 as common. 9 into 1 equals 9, 9 into 2 equals 18, and 9 into 3 equals 27. So we are going to write it as 9 into 1, 9 into 2, and 9 into 3. Then this column, it has 27 as common. 27 into 1 is the first element of this column. Then 27 into 2, which is equal to 54, is the second element, and 27 into 3, which is the third element of this column. And then we have 36, 24, and 28 as it is. And this is equal to 0, so we are going to remove this first equal sign. Okay. Now, whenever a constant is common in the entire row or the entire column, we can write it as a common of the whole determinant. As this 9 is common in this entire column, so we can write 9 over here as the common element, and we'll do the same with 27. So 9 into 27. We have brought them outside of the determinant matrix, and inside we are just left with these numerals. So we have 1, 2, and 3 over here left, and 1, 2, and 3. And then we have 36, 24, and 28 as it is. And this is equal to 0. Now, as you can see that two columns are the same, 1, 2, and 3, 1, 2, and 3, they are repeating. So whenever two rows or two columns in a matrix or in a determinant matrix are equal, then we know that its determinant will be equal to 0. So we are going to use these properties to prove it equal to the right hand side. So right hand side is 0. This hand side will become 0 because of these two same columns, and therefore we have proved this first question. Now when coming to the second question, this is the second part of the same question, question number 1. So we have 1 by A, 1 by B, and 1 by C, then BC, AC, and AB, and then these three elements. Now, as we can bring the an element out of the determinant matrix, we can introduce a new element into the matrix as well. But to introduce an element, we are going to multiply it with the entire row, so we also have to divide it. Okay. For example, here I'm going to multiply the first row with A, the second row with B, and the third row with C. You'll see the result that why am I doing this in a few steps. But first of all, see that when I do this, I cannot just multiply A, B, and C as I've written. I will also have to divide it to balance the entire equation. Okay, here comes C. Okay, now we are going to multiply and divide A, B, and C. Okay, so we have A by A into B by B into C by C with this entire determinant matrix over here. So we have 1 by A, 1 by B, and 1 by C. Then we have BC, AC, and AB. And we have B plus C. Then we have A plus C and A plus B. And this is equals to 0. Now we are going to multiply this A with the first row, this B with the second row, and this C with the third row. And these divided A, B, and C will remain as it is over here. So it is going to be like 1 by A, B, C into... Now multiply A with this entire row. So we have A by A, B, C, and A into B plus C. Then we have B by B, okay, B by B, A, B, C, and B into A plus C. Then we have C by C. We are going to multiply C with the third row. So A, B, C, and then C into A plus B. and this is equals to 0. Now we are going to cancel these terms. Okay, and we can take ABC common from all of these terms. So we are going to bring this ABC outside of the determinant matrix, and these will be cancelled to be 1. So we have 1 by ABC, and then 1, 1, 1. This ABC is brought over here, so we are going to write it as A, B, and C. Then we have again 1, 1, and 1 because we have taken it common. And then we have A into B plus C. This entire column will be written as it is, okay? Okay, we can cancel these, and we know that both of these columns are same. They are equal to one another, 1, 1, 1, 1, 1, 1. They're repeating, so it is going to be 0. The determinant of this matrix is going to be 0, and this is equal to the right hand side, and so we have proved this one also. Now we are going to solve the third part, which is 0 minus A minus B, then A 0 and minus C, and B C and 0, and we have to prove it equal to 0. This part is proved by the use of another property, that is that if a matrix is skew symmetric, which we have discussed in previous exercises, and it has an odd order. These two are must. If a matrix is skew symmetric and it has an odd order, then its determinant must be equal to 0. Now, what is order? Order is the number of columns of the matrix, or number of rows and columns of the matrix. So it is its order is 3 cross 3, which is odd. 3 and 3 are odd. So this is already odd, and it is a skew symmetric matrix. How are we going to see this? We can take its transpose. A matrix A is skew symmetric if the negative of that matrix is equal to its transpose. So we are going to prove that this is a skew symmetric matrix by finding the negative of this matrix, of this determinant matrix, is equal to what, okay? So minus A 0, C minus B minus C and 0. Now multiply this negative with the entire determinant matrix. So we have 0 minus A minus B, and then we have A 0 and minus C, and then B, C, and 0. So this is the resulting matrix of negative. This is negative A, this side, and then we have to find the A transpose of this determinant matrix, which is going to be, we are going to write this row into the form of columns. So 0 minus A minus B, then we have A 0 C and negative C, and then we have B C 0. So this is A transpose, and we can see that these two are equal. So as these are equal, therefore this is a skew symmetric matrix. And for a skew symmetric matrix and a determinant matrix that has an odd order, we can say that its determinant is going to be 0. So this is also proved. So for this fourth part, we must know about all the trigonometric formulas that we have. So the first one is sine square theta plus cos square theta equals to 1. Then another is tan square theta plus 1 equals to secant square theta, and cot square theta plus 1 equals to cosecant square theta. Now we are going to use all of these formulas over in this question, part number 4. So it's over here. Okay, now we have to solve it. We are going to learn another property, that for determinants we can add any two columns and any two rows, given that we are adding or subtracting or whatever we are doing. We have to do it with all the rows and all the elements of those rows, okay? So here we are. Sine square alpha plus cos square alpha will give us 1. So we are going to add these two columns to give us this result. This as a result and this as a result, okay? So we are going to write it first, adding column 1 and column 3. So we have sine square alpha a plus cos square a. Then we have tan square a plus 1. And then we have 1 minus cosecant square a. And then we are going to write the rest of the columns as it is. 1 secant square a and then minus cot square a. And we have cos square a 1 and 1. It is equals to 0. Okay. Sine square a plus cos square a equals 1. So we are going to write 1 in its place. Then tan square a plus 1 equals to secant square a. We are going to write it as it is as well. Then we have 1 minus cosecant square a. So if this 1 remains here, 1 minus this cosecant square theta comes over here. Cosecant square theta is equals to minus cot square theta. So this is the new formula we have derived from the previous one. So 1 minus cosecant square a equals to minus cot square a. So minus cot square a. Then we have 1. The rest of the elements will be written as it is. Okay. Cot square a, then cos square a, 1 and 1. It is equals to 0. As this column and this column are same, 1 secant square a and minus cot square a is repeated over here as well. So this determinant is 0 and this is equal to the right hand side, and we have proved this part as well. Now coming to the fifth part, there are cube formulas over here and over here, and then we have these terms. So what we are going to do is that we are going to open these cube formulas. Okay, the formulas are a minus b whole cube equals to a cube minus b cube minus 3ab into a minus b. Then we have a cube minus b cube. It is equal to a minus b into a square plus ab plus b square. Okay, now we are not going to open this bracket. We are just going to open this formula. Okay, there is some reason behind it which you'll understand later on. So we have a minus b whole cube, c minus d whole cube, and e minus f whole cube. Then we have a cube minus b cube. We are going to use this formula and write it as a minus b into a square plus ab plus b square. Then we have c minus d into c square plus cd plus d square. Then we have e minus f into e square plus ef plus f square. And we are going to write all of them as it is. ab into a minus b, cd into c minus d, and ef into e minus f, which is equals to 0. Now we are going to take this common, a minus b, and a minus b, and all of such elements common. So we are going to have a minus b into c minus d and e minus f as common. And inside the determinant matrix, we are going to have a minus b whole square, c minus d whole square, and e minus f whole square. Then we have a square plus ab plus b square, c square plus cd plus d square, and e square plus ef plus f square. And we have ab, cd, and ef, and this is equals to 0. Now for the next step, we are going to write, these terms are going to be written as it is till the end, a minus b into c minus d into e minus f. And now we are going to open these square formulas. Okay, I must write them over here too. A minus b whole square equals to a square minus 2ab plus b square. So we have, now it is going to be a square plus, no, it's going to be minus 2ab plus b square. Then c square minus 2cd plus d square, and e square minus 2ef plus f square. and then all of them written as it is: a square plus ab plus b square, then c square plus cd plus d square, and e square plus ef plus f square. And a, b, c, d, and e, f is equals to 0. Now what are we going to do? Now if we subtract, not subtract, basically add, not add, basically subtract, okay. Now, if we subtract this column with this column, so what will happen is a square will cancel with a square, b square will cancel with b square, and we will be left with minus 2ab and minus ab. So it will become minus 3ab, this will become minus 3cd, and this will become minus 3ef. Minus 3 will be taken as common, and we will be left with a, b, c, d, e, f, which is this column as well. So we will get two same columns, and the determinant will be 0. So we are going to execute our plan by writing subtracting column 2 from column 1, and we have a minus b into c minus d into e minus f, and then we are going to subtract it as a square minus 2ab plus b square, and we are going to subtract this column minus a square minus ab minus b square, and then the rest of it is going to be written as it is: a square plus ab plus b square and ab. Then we have c square minus 2cd plus d square minus c square minus cd minus d square. Then c square plus cd plus d square and cd. Then we have e square minus 2ef plus f square minus e square minus ef minus f square, e square plus ef plus f square and ef, and this is equals to 0. Then we have a minus b into c minus d into e minus f. Let's cancel what can be cancelled. A square minus a square, b square minus b square, c square minus c square, d square minus d square, e square minus e square, f square and minus f square. And we are left with minus 2ab minus ab is minus 3ab minus 3cd and minus 3ef. The rest are going to be written as it is. Now we are going to take minus 3 as common, so minus 3 into a minus b into c minus d into e minus f, and we are left with a, b, c, d, e, f. Then the rest is again going to be written as it is. Now this column and this column are exactly same, that's why it is going to be 0 in the determinant of this determinant matrix, and it is already 0 over here, so we have proved the fifth part as well. So this is the sixth part. Now how are we going to solve this and prove that this side is equal to 0? We have to multiply the first row with, okay, let's write it side by side. Multiply first row with, there is no y over here, so we are going to multiply it with y. Then the second row with z, and the third row with x. Now let's multiply it, the first row with y, so it will become xy minus yz and 0. Then the second row with z, so we are going to have 0, yz and minus xz, and the third row with x, so we are going to have minus xy, 0 and xz. Now as we can see that by adding these rows, we are going to have 0. Let's see. If we add the first row, r1 plus r2 plus r3. Okay, we are going to do this. Okay. Now if we add this row with this row and this row, we are going to have xy minus xy, which is equal to 0. Then we are going to have minus yz plus yz, which is equals to 0. And then we are going to have 0 minus xz plus xz, which is also equal to 0. So we are going to write it over here as the next step, which is xy minus xy. Then the rest of the rows will be written as it is. Okay. Now this one will be minus yz plus yz, and then we have yz as it is and 0 as it is. Then we have 0 minus xz plus xz, and then we have the rest of the rows written as it is. Now we are going to cancel them, and we are left with a complete row of zeros. And let's write the rest of the rows. Now when we have a complete row of zeros or a complete column of zeros, which we are not having right now, but it's just an information that if we have a complete row or a column of zeros, then we are going to write that the determinant of this determinant matrix is going to be 0, which is equal to the right hand side, and hence we have proved this. Now let's do the last part, which is a minus b whole square, a plus b whole square, and ab, and so on. Okay. Now first of all, write the formula of x minus y whole square is equals to x square plus y square minus 2xy, and then we are having x plus y whole square, which is equals to x square plus y square plus 2xy. Now to solve this question, we need these two formulas, and we are going to open all of these brackets using those formulas. So we have a minus b whole square, we are going to write it as a square plus b square minus 2ab, and then here we are going to write a square plus b square plus 2ab, and then ab, and it is equals to 0. Now let's do the same with the rest of the rows as well. Okay, now what are we going to do is we are going to add up, not add, basically we are going to do this: column 1 minus column 2. So we have a square plus b square minus 2ab minus a square plus b square plus 2ab, and the rest of the columns will be written as it is. So we have a square plus b square plus 2ab, and then ab, it is equals to 0. Now let's do the same with the rest of the rows. Now let's open these brackets. We are going to write them as a square plus b square minus 2ab, then minus a square minus b square minus 2ab. Then we have the rest of the columns written as it is. And we are going to follow the same pattern for the rest of the rows as well. Now we are going to cancel the terms that can be cancelled. So we have these terms cancelled. Oops. Okay. Now minus 2ab minus 2ab gives us minus 4ab. Minus 2cd is minus 4cd. Minus 2ef and minus 2ef is minus 4ef. This column will be written as it is: a square plus b square plus 2ab, c square plus d square plus 2cd, and e square plus f square plus 2ef, and then a, b, c, d, and ef, it is equals to 0. Now we are going to take minus 4 common over here, so we are going to have minus 4 into a, b, c, d, e, f, and then a square plus b square plus 2ab, c square plus d square plus 2cd, and e square plus f square plus 2ef. Then a, b, c, d, and ef, it is equals to 0. These two columns are exactly same, and when two columns are exactly same, we are going to write that the determinant of this determinant matrix is 0, which is equal to the right hand side, and we have proved the last part as well. Thank you.